we now define the exterior derivative on a manifold. As most definitions on manifolds go, we first define it on local parametrizations and sort of say that this gives a global definition. So let's get on with the definition. So M is a smooth manifold. M is a smooth manifold and omega a K-form on M. So what we do is we define what this derivative is going to be on a parametrization. So let phi from U to M be a local parametrization. On the image of this parametrization, we are going to define the derivative. We already know how to do it on open sets in Euclidean space. So what you do is you look at this form omega restricted to this open set of restricted to the image of this parametrization. So look at phi restricted to omega restricted to phi of U, then pull it back under phi. Then you are now left with a form in Euclidean space which you can differentiate. That will give you a k+1 form on U. Now just pull it back now by F inverse star. Okay, this would give you a form defined at least on the open set, not the open set, defined on the set phi of U. It will be a k+1 form on phi of U. But the problem is you could have taken some other chart and done the same thing, not chart, you could have taken some other local parametrization and done the same thing, and you would have been left with an answer that could possibly be different from the answer we have here. So more precisely, let psi from V to M be another parametrization, such that psi of V and phi of U intersect. So we are in this situation where we are going to consider two local parametrizations whose images overlap. This would give you two forms, two different, possibly different forms on the overlap. So what we have essentially got to check is this complicated expression phi inverse star of d phi star omega. And if you don't mind, I'm going to stop writing the restrictions of the form to the appropriate sets because it's self-evident which set we are talking about. We have to show that this is same as psi inverse star d psi star omega on the overlap psi of V intersect phi of U. On this overlap, both of these are defined and we have to show that both are equal on this overlap. But we know that we have a nice property of pullback and the derivative operator. It is that they commute at least on open sets. So what you do is you set G to be phi inverse composed with psi. And again, I'm not going to write down what the domain of definition of this function is. It should be self-evident to you and you should write it down when you take your notes what exactly the domain of G is. Okay. Now the previous in the previous video we saw that pullbacks and derivatives behave very nicely. So you look at G star d phi star omega d G star phi star omega. Okay, this is nothing but d of psi star omega. You just apply the previous corollary to this complicated expression on the left, you would get it. Of course, I have also used the chain rule for pullbacks in this previous computation, which I am just skipping. Okay, so just check that this is true. Using this, we get that psi inverse star of d psi star omega is psi inverse star G star d phi star omega phi star omega, which is just phi inverse star d phi star omega. Again, I am skipping where these things are defined. I leave it to you to find out the evident domains of definitions of these objects, and this shows d omega is well defined. Irrespective of which local parameterization you choose, you invariably end up with the same k+1 form on the open set. Is a well defined k+1 smooth form. K+1, or rather smooth k+1 form is a better way of writing it. Well defined smooth k+1 form on M. Okay. Now given the fact that we have various simple properties of the exterior derivative on open sets, it should not be surprising that the same results are also true for manifolds. Let me just state that result and leave the routine verification to you. This is the exterior derivative d on manifolds enjoy the following properties. Enjoy the following properties. Number 1, linearity. Number 1, linearity. D of omega 1 plus C omega 2 is D omega 1 plus C D omega 2. Okay. Then behavior under the wedge product, which just says that d omega wedge eta is d omega wedge eta plus minus 1 power k omega wedge d eta, where omega is a k form. And number 3, d of d omega is 0. This is that co-cycle condition. Then the fourth one, it says that if f from M to R is a function, then the one form df is same as the map df, where dfa is a map. This is the map from TAM to R viewed as a one form. On V equal to TM. Dual vectors are one forms. Okay. Finally, the fifth property is if G from M to N is a diffeomorphism of manifolds. Diffeomorphism of manifolds just means that you have smooth maps in both directions. That is, G is bijective, smooth onto N, and G inverse is also smooth. Then D circle G star is G star circle D. All of these properties follow immediately from the corresponding properties on open sets, because the exterior derivative on manifolds was just defined via local parameterization by translating everything into Euclidean space. So just check a few of these and it will become obvious to you that the rest are utterly straightforward. So this concludes most of the machinery we need to state Stokes' theorem. We will state Stokes' theorem in the next video after seeing briefly manifolds on boundary. After that, we will state Stokes' theorem. This is a course on real analysis, and you have just watched the video on exterior derivative on a manifold.